Hi, I'm Elena, and today I'm going to introduce a new way to solve Chinese remainder problems. If you love math and really enjoy challenging yourself, you might come across a problem that looks like this. What is the smallest positive integer that has a remainder of 2 when divided by 5, a remainder of 3 when divided by 7, and a remainder of 10 when divided by 11? These kinds of questions are known as Chinese remainder problems. There are many ways to solve them, and one of the most common ways is using the Chinese remainder theorem. However, if you don't know what the Chinese remainder theorem is, or you don't understand it, or you have a hard time remembering it, don't be frustrated. I found out a new method that's easy, simple, and intuitive. All you need to know is the LCM, which is the least common multiple, and you also need to know a little bit of modular arithmetic notation. So modular arithmetic notation looks like this. 7 is congruent to 1 modular 3. This is just an example, and in this case, we can get that this means that 7, when divided by 3, is something, which we don't really care about in this case, with a remainder of 1. As you can see, this 1 corresponds to this one over here, 3 corresponds to the 3 over here, and 7 corresponds to 7 over here. Okay, another thing you need to know about is when you have a number, say x, and x is congruent to 0 mod n. This means that x is a multiple of n. Now you have another one that says x is congruent to 0 mod m. This second one tells us that x is also a multiple of m. So then these two show us that x is a common multiple of n and m, which can be rewritten as x is congruent to 0 mod the LCM of n and m. This is a very key important thing in my method, so please keep this in mind. Okay, now let's get back to the question. So once again, the question is, what is the smallest positive integer that has a remainder of 2 when divided by 5, a remainder of 3 when divided by 7, and a remainder of 10 when divided by 11? From our first piece of information, we can get that x, that is if we let our original number, the smallest positive integer here, if we let that one be x, then our first piece of information tells us x is congruent to 2 when divided by 5. And our second piece of information says that it has a remainder of 3 when divided by 7. So we write it as x is congruent to 3 mod 7. And our third piece of information tells us x has a remainder of 10 when mod 11. So our goal is that if we want to eventually have a magic number n added to x, so that it is congruent to 0 mod 5. It's also congruent to 0 mod 7, and it's also congruent to 0 mod 11. So our goal is to find this magical number n, and as we add the numbers, we're going to keep track of what we added and what our n will be. So let's continue. Remember, we have x is congruent to 2 mod 5, and x is congruent to 3 mod 7, and x is congruent to 10 mod 11. Now, let's look at the first equation. So then we want to add something to x to make it congruent to 0 mod 5. And as you can see, there is a 2 over here. So since we have the 2 over there, we know that we should add 3. And as you can see, this is equal to 5, right, if we simplify it. And 5 divided by 5 has a remainder of 0. This means that we can simplify this to, we can get rid of that part and get rid of it. So we have 0 over here instead. Now we're going to add 3 to the other two equations. Now this part we can simplify it to 6. We can simplify this to 6. And here we can simplify this to 13. Okay, now let's look at the second equation. And because we already have a 0 over here, we don't want to change that. So we're going to keep adding multiples of 5. But keep in mind that if it's too hard to add, you can also try subtracting, as long as it's an integer multiple of 5. So in this case, let's try adding. So, okay, let's try starting from 6. Let's try adding a 5. We get 11. That's definitely not a multiple of 7. So we're going to add another 5, and we get 16. That's still not a multiple of 7. So we're going to add another 5. You're going to add another 5, and you get, this is 21. 21 is a multiple of 7. So we can add 3 times 5 here. And then if you add this, we already said that that was 21. And 21 divided by 7 has a remainder of 0. So we can simplify that. And we have that this is now 0. And then we're going to, of course, add 15, or 3 times 5, to the third equation. So yeah, we can simplify this part into 13 plus 15. We get that that's 28. 28 divided by 11 has a remainder of 6. So we will replace this with 6. Okay, now as you can see here, both of them are 0. So we're going to merge these first two equations together. As a result, we will have something that looks like this. Remember to simplify it as always. But for the sake of this, we're going to keep 3 times 5. For you to see that this is the same. But in reality, you should always simplify. That's not enough space. Okay. Remember the key point I've mentioned before. Here we're using it again. And we're going to keep the third equation the same, right? So it's just now, as I've said, you should always simplify. So we can simplify this part to 35 because 7 and 5 are coprime and the LCM of two coprime numbers are their product. So we should rewrite that as 35. Okay, now as I've also said before, since it's a 0, we don't want to change it. So that means that we're going to have to add multiples of 35. We can also subtract multiples of 35 if it's too hard. Let's first start with adding. If we did 6 and we added 35, we'd get 41. 41 is not a multiple of 11. Then we add another 35 and we get 76. 76 is still not a multiple of 11, so we're going to add another 35 to that. So we're going to add another 35 to 76. And we get 111. And if we tried to keep adding more, it would take a really long time to get the right number. If we did 111 plus 35, we'd get 146, and that's still not a multiple of 11. So maybe instead of doing this, why don't we try subtracting instead? So instead, we're going to try subtract. So let's do 6 minus 35. And this is equal to negative 29. Now we're going to subtract another 35. And we get negative 64. And then we're going to subtract another 35 because negative 64 is still not a multiple of 11. And we get negative 99. And negative 99 is a multiple of 11, so we are going to subtract 3 times 35 because, as you can see, we had 3 negative 35s here. So we're going to subtract 3 times 35. And this part, remember, still stays 0 because we added a multiple of we subtracted a multiple of 35. And we're going to do that to this one. And remember, since negative 99 is a multiple of 11, we can change this to 0. Okay, now once again, we are going to merge these two together. And merging the two of them together will now result in something that looks like this. X plus 3 plus 3 times 5 minus 3 times 35 is congruent to 0 mod the LCM of 35, and 11. Okay. Okay, now let's simplify now, remember. So this part we can rewrite it as x minus, we can rewrite it as x minus. So we have 3 times 6 minus 3 times 35, and we can rewrite this as negative 87. And then this is congruent to 0 mod, what's the LCM of 35 and 11? Because they're co-prime, then it's those two numbers multiplied together. It's 385. Okay, now we're going to add 87 on both sides. So we get x is congruent to 87 mod 385. And since we're looking for the smallest number, if you recall the question, then 87 would be the smallest positive integer. So as a result, we have that x is equal to 87 as our answer. Okay, so if we were to generalize our method, if we had, okay, x is congruent to, I'm gonna give it a little more space. So let's do this. Let's give it a little more space. Okay, if we had x is congruent to a1, okay, mod n1, and then x is congruent to a2 mod n2, and x is congruent to a3 mod n3, and all the way to, let's assume that we have k of such items, so we have x is congruent to a k mod n k. Then this is how our method would work. So you would add n 1 minus a1. Okay, then you're going to clean this thing out, and it would be 0. And you're going to add this to all of them. Okay, now next, as I've also said a long time before, this is 0, we don't want to change it. So we're going to add a multiple of n1 and say, let's pretend the first time we multiplied was m1 times n1, okay? So we'd have plus m1 n1. This is still 0, remember. Then plus m1 n1. We're going to add m1 n1. And we added m1 n1 so that this part here, do it with red, this part here is supposed to be 0. So let's get rid of that and change it to 0. And that should be 0. Next, we're going to keep adding this to the others because that's what we should do. So M1, N1, and this one you're going to add M1, N1, and add M1, N1. Okay, now we're going to suppose to merge these two together. So we can merge those two together, yes. So let's get rid of this. And instead of having it like that, we're going to change this part into mod the LCM of N1 and N2. Now, once again, we want to keep the 0 here, so we're going to add a multiple of the LCM of N1 and N2 to here, so that it becomes 0 here. So we're going to add something that looks like, let's do M2 times the LCM of N1 and N2, and then this part will become 0. Okay, and then we're going to make sure, remember, you have to add the other things over here. The other things over here down here. So we're going to add M2 times the LCM of, scroll down a bit. I'm going to add L times the LCM of N1 and N2. And we're also going to do that over here. So M2 times the LCM of N1 and N2. And you're going to merge these two together again, and then keep repeating the steps until you get down to the right side of the last equation will become 0 eventually. And that is the generalization of our method. And because since we're using LCM here, this also applies to, we don't need N1 and N2 to be, we don't need N1 and N2 all the way to NK to be like relatively prime. They can still have some common factors because we're using the LCM here. So that was my new method for solving the Chinese remainder problems. I hope you enjoyed it, and thanks for watching.